Hi, this is Mr. Cure, and welcome to this video on Newton's second law. So we've already developed some of the relationships in Newton's second law through the gizmo we looked at earlier. So I thought I'd just look at some examples and review some of the parts of this second law note. So first of all, we already know this as well. The first component here, number one, that if we got an unbalanced force, in other words, an overall F net force acting on an object, the object accelerates in the same direction as the F net. So here, I've got all these forces acting on this vehicle, and when you add all of the forces up, the sum of the forces is going to be 150 newtons towards the east. I guess we have east over here. And what's going to happen is the acceleration is going to be in the eastward direction as well. What we also know, we developed with the gizmo, is that if the mass of the object is constant, it's the same object, as my force gets bigger, we have a larger acceleration. Makes sense. So if you've got more of a push, you can move something a lot faster. You can accelerate it more. So this is called a direct proportionality. So the two variables do exactly the same thing. And I can write down the symbol. It's like a fish symbol, proportional symbol. So the acceleration is directly proportional to the overall net force acting on it. So remember, this symbol means directly proportional. So as one increases, the other increases in this case. We also already know that if my object changes, the acceleration will change. So here I've got the same push, the same force, but what happens is my mass gets bigger. And as the mass gets larger, it's the same push, well, it's going to be hard to move the object, so the acceleration is actually going to decrease. They do opposite things. So to show that, we use this proportionality. So acceleration is inversely proportional to the mass. So as my mass gets bigger, the acceleration does the opposite. So again, in this case, this is an inverse or relationship or proportionality. So what we're going to do now is we're going to combine all of these together. So you notice I had numbers up here. So number one, again, we talked about the object accelerating in the direction of the F net, the net force. Well, that's what we have here. And then the acceleration is directly proportional to the amount of net force. So it's number two up here. And number three, the acceleration depends on the mass. It's inversely proportional to the mass. So this would be the third part. And what we can do is we can take all of these, combine them, and come up with a relationship. So let's take a look. So first of all, the sum of the forces is called the F net. So this is the unbalanced force. We also have our mass, and we have our acceleration. And here's what we know so far. We know that the acceleration is directly proportional to mass. It's inversely proportional to mass, and it's directly proportional to the F net. So I can combine these two relationships. So the acceleration is directly proportional to the overall unbalanced force and inversely proportional to the mass. And I can change this into an equation. So the acceleration, let me just write it down over here. So the acceleration of an object is equal to the overall unbalanced force divided by the mass. What we normally do, though, is we look at the equation like this, but oftentimes we find the equation looking like this. So the F net, the overall force, is equal to the mass times the acceleration of an object. Again, it's the exact same thing, just a different way of writing it. Well, let's look at the variables we have here. So when I look at the mass, I measure mass in kilograms. Acceleration we measure in meters per second squared. And newtons are what we use to measure forces in. So what we have here is a newton being equal to a kilogram meter per second squared. So this is just another way of writing the newton in some more fundamental units. Though we could write it like a kilogram meter per second squared. Usually we write it down as newton. Okay, now let's look at a question, a very simple example involving this relationship and this equation. So recall what we had earlier is a whole bunch of forces acting on this vehicle, and the sum of the forces acting on it was 150 newtons towards the east. And let's assume that the mass of the car is 2,180 kilograms. Well, what if I want to know the acceleration? Well, what I know is the following. I know I've got my equation for second law. The acceleration is equal to the net force over the mass. I know both those values, so I can substitute it in here, and now we can find how much we're actually accelerating. So it's a really, really neat application of this particular law. So then you have an acceleration of 0.069 meters per second squared to the east. So now we know how the motion of the vehicle is going to be changing. Just one quick thing, and remember here, had a Newton over a kilogram. Just make sure the units work out. Now remember, the Newton is equal to a kilogram, meter, all over second squared, and all of this is over kilogram. So when I cancel out the kilograms, what you're left with is meters per second squared. And that's exactly the correct unit over here. So I just wanted to show you how we can use the unit cancellation to verify some of the units. Now, what we're going to be doing is we're going to be looking at some examples using free body diagrams on the next few pages. So just stay tuned.